Good morning, my dear friends. I hope you all are doing great. So today our topic is relationship between delta H and delta U for a gaseous reaction at constant pressure and temperature. Before we look into that relationship between delta H and delta U, let us try to understand some basic points here. Look here, my dear friends. Most of the solids and liquids are incompressible. That means if you take solids and liquids, my dear friends, you cannot compress them. If you try to compress solid and liquids, let us suppose, then there will be a change in value, but that change in value is almost negligible. Why it is so? Have a look here, my dear friends. Let us suppose we have a solid here in this particular closed system, and this is the piston right out here. And I am applying pressure onto these molecules. These are the molecules of solid. Correct or not? So my dear friends, the space between these molecules is almost negligible. That means between these molecules, if you see, the space is almost negligible. So if you try to compress it, are you able to compress it or not? You are not able to compress it. Reason? Because the spaces between the molecules is almost negligible. Okay? Now look at the liquid. The molecules are little bit away from each other. Little bit. Very small distance between the molecules. So if you try to compress these molecules, they will come closer. Let us suppose two molecules are little far away from each other and you compress them, they will come closer. But remember here, the volume change in liquids will be there, but it will be almost negligible. That means there will be a very small change in the volume in case of liquids. And what does it mean? That means that change in volume is that much small or differential small that it can be neglected. So when we talk of the change in volume here, it's very small in case of solids because space is very much negligible between the molecules. But here there is a little space between the molecules, so you can compress it. But when you compress it, the volume will change. But that change is again differential. Yes, but slightly bigger than the solids. But when we look at the gases, look at the gaseous molecules. Gaseous molecules are very far away from each other. So if you try to compress the gas, there will be a very large change in value. So remember that particular point. If you try to compress a solid, between molecules, the space is almost negligible. So compression will be very less in solids. So we can take that as zero, almost zero. Or we can take that as almost differential, we can take it as. Or we can take it as insignificant, not important. But when we look at the liquids, there is a change in volume, little greater than solids, because there is a gap, there is an intermolecular space in liquids. But that intermolecular space is almost, very less. That is also called as differential space. That means change in volume will be in liquids greater than solids, but this change is also not that much important. It is also a differential change only. So this will also become insignificant change. But when we apply pressure on the gaseous molecules are far away from each other. So when you apply the pressure on them, they will come closer. So the change in volume will be very large. Look at, on compression they will come very close, so change in volume will be very large. So I have written some points here, my dear friends. Most of the solids and liquids are incompressible. Yes? The volume change in solids and liquids on applying pressure onto them is almost negligible or insignificant. That means volume change here and here is that much small that you neglect it. So we call it as insignificant change in volume. Correct? But when we talk of gases are highly compressible because in gases there exists large intermolecular spaces. Okay? When pressure is applied onto the gas, the molecules come closer and hence the volume change is significant. So my dear friends, the change in volume is large in gases. So here the change in volume is significant. But here in these two cases, the change in volume is insignificant in solids and liquids. But in gases here, the change in volume is significant, means large change will be there. So this is important change and this is not important. Why it's important? Because change in volume is here. It's a differential change. Differential change basically means almost negligible change. Almost negligible. But here significant. Why? Because there is a large change in volume. And now you will be talking about that. Why sir is talking about pressure and volume? Because my dear friends, in thermodynamics, we are concerned about pressure volume work. Pressure volume work. So that's why I am talking about pressure with respect to change in volume. Yes or no? So my dear friends, remember always, in solids and liquids, the change in volume is almost negligible. Yes? But, or we can say it is insignificant, not important. But the change in volume in the gases on applying the pressure is very large. The change in volume is very large. So we call it as significant. So this change in volume is significant. Remember that point. So when you have understood these points here, okay, now we will start our topic after this called as relationship between delta H and delta U for a gaseous reaction at constant pressure and temperature. Please make note of this. Dear friends, now after understanding that the volume change in solids and liquids is almost negligible, or we call it as insignificant when we apply pressure onto solids and liquids, correct? So in the same way, when we apply pressure onto the gases, the change in volume is significant. That means there's a large change in volume, correct? So let us have a look here now. Relationship between delta H and delta U for a gaseous reaction, but we are keeping two things constant here, pressure and temperature. Remember that particular point. So, my dear friends, let's talk about initial state and we'll talk about the final state of a system. Before we talk of initial state and the final state, let us take one chemical reaction here. Just a rough idea. Let's suppose I will take A plus B gives me C. This is gaseous, gaseous and gaseous. These two are your reactants and this is your product, my dear friends. Now if we talk about the initial state of that gaseous reaction, my dear friends, gaseous reaction we have here going on. Let's talk about the initial state of it. In initial state, everybody knows that P is constant. Two things are constant, so we will not change the pressure here. Pressure is constant. Temperature is also constant. Two things are constant. Okay. What happens here, my dear friends? If I talk of volume now, okay, here and here. When reactants are changing into products, you can see here, my dear friends, here we have 2 moles. We have 2 moles of reactants here. And I am getting here 1 mole of products. That means number of moles are changing, my dear friends. How many moles we have here? N stands for number of moles. Number of moles of reactants. We have here, let us suppose, 2 moles. Okay. And these are the number of moles of products. And here we have only 1 mole of the product. And remember, this reactant is in gaseous state and this product is also in gaseous state. So how many moles we have here? 2 moles. And how many moles we have here? 1 mole. We are carrying out this reaction in a particular closed system. Let us suppose where the reactants are changing into the products. And the reactants we have 2 moles and products we have 1 mole. So 2 moles are changing into 1 mole. When 2 moles will change into 1 mole, understand the number of moles are decreasing. And when number of moles are decreasing, understand that the volume will also decrease. So here, when we move from here to here, I will write down number of moles are decreasing. From reactants to products. From reactants to products. So you are moving from 2 moles to 1 mole. This is your reactant and these are your reactants and this is your product. So number of moles are decreasing from reactants to products. When number of moles are decreasing, then what will happen? Volume of the system in which chemical reaction takes place. In which chemical reaction takes place will also decrease. So let's understand it. I am taking a gaseous reaction, my dear friends, in a closed system, correct? Which is fitted with the piston, correct? And now external pressure is kept constant and temperature is also kept constant. So what is happening? A chemical reaction is happening. 2 moles of gases A and B are changing into 1 mole of C. Yes? So here we have 2 moles of reactants changing into 1 mole of product. So now when reactants change into products, number of moles are decreasing. So here we have 2 moles are changing into 1 mole. So number of moles of the, in the process are decreasing. That means from reactants to products, reactants are 2 moles, product is 1 mole. That means number of moles are decreasing when reactants are changing into products. That is from 2 to 1. Correct. When number of moles will decrease, yes, then what will happen? Volume of the system in which chemical reaction takes place will also decrease. Why? 2 moles will occupy more space and 1 mole will occupy less space, or we can tell 2 moles will have more volume and 1 mole will have less volume. So that means when 2 moles are changing into 1 mole, that means the more space occupied by the moles is changing into the less space occupied by the moles. That means more volume is changing into lesser volume. Correct? So that's why I wrote the volume of the system in which chemical reaction takes place will also decrease. Number of moles are decreasing, volume will also decrease, because number of moles, we will write down a relationship here. Number of moles is directly proportional to the volume. If more number of moles you have, more is the volume. If number of moles will increase, volume will also increase. But here the number of moles are decreasing from 2 to 1 and volume will also decrease. Yes. So let's come to the point now. So volume is decreasing. You can see there the volume is decreasing. Let us suppose the initial value is Vi, you can write down, or you can write down, let's suppose Va is the initial value. Let's suppose the initial state is A and final state is B. Then I can call it as Va. You can write down Vi also, Vx also. But you have to remember that the initial state, this is initial state. And volume is changing. Let us suppose volume has changed from Va to Vb. And we know that volume will only change when number of moles will change. Number of moles are changing from 2 to 1. That means number of moles are decreasing. So let's suppose here number of moles are here what? Na, and here the number of moles are Nb. And 2 things are constant here, my dear friends. Everybody knows here, for this pressure and temperature are constant. These 2 are constant, my dear friends. So now, my dear friends, you have understood that volume is changing and the number of moles are changing. Yes. So now, if we use ideal gas equation for initial state, my dear friends, for initial state A, okay, what will be the ideal gas? Let us use ideal gas equation. Okay, then we have So what we will have, my dear friends, have a look. We know that ideal gas equation is PV is equal to nRT, my dear friends, that's ideal gas equation. And we know that in initial state what is happening? Volume is VA. So in place of this we'll write down VA. And you know that pressure is constant, so pressure will be constant only, correct? Temperature is constant, so temperature will be constant only. And R is also constant because it's a universal gas constant. But number of moles at initial state are what? Come on, Na. So we have here Na. So only these two things are changing, volume and number of moles. This guy is constant. This guy is constant. Yes. Now this volume is changing from Va to, come on, Vb. And number of moles are changing from Na to Nb. And rest of the things are constant. Even this guy is also a universal gas constant. Correct? Let us talk about now final state. For final state, which is B. Okay? Same thing I will do. Let us use ideal gas equation. Then we have. So what we will have at the final state, my dear friends. Same thing we will have here also. We'll be having here PV is equal to nRT. So in final state we know that volume is PV. Yes. And the number of moles are Nb. Correct? So now, my dear friends, this is constant. These two are also constant here. But volume has become now Vb and number of moles have become Nb. Now you look here at the initial state. Pressure and pressure both are constant. Temperature and temperature here, these both are constant. So here three factors are constant. P, R, T are constant, and here also P, R, T are constant. So my dear friends, here P, R, T, they are constant. And again here P, R, T are constant. So these three factors are constant. Correct? So now this is the initial state, okay? And this is the final state of the system. Which system? The system in which gaseous reaction is taking place. Then, in order to calculate the total change, we always take it from final minus initial. So this is the final state and this is the initial state of the system in terms of ideal gas equation. We can call it as, let us suppose this is now equation number 1 and this is equation number 2. This is the equation of ideal gas for the initial state and this is the equation of ideal gas for the final state of the system. Now my dear friends, you make note of them and I will discuss them further. Please make note of this. Now dear friends, for initial state A, regarding a gaseous reaction taking place in a particular system, correct? We have one equation with us. PVA is equal to nRT, that is NaRT. That's equation number 1. We have just derived it. And then for the final state of the system. So for final state B, we call it as, we have PVB is equal to NBRT, that is second. Okay. Now we can do that, subtract first from second. If we subtract first from second, we will get what? Final minus initial. So obviously I can directly write down now here. Try to understand. This is the final state. Whenever we calculate, let us suppose change in value, we are calculating final minus initial, we are calculating change in temperature, final minus initial. That means all are state functions only or not? Same is the case here. This is final state. So tell me what is the final state here? PVB is a final state. What is the initial state? PVA, so minus PVA. Correct? Tell me, what is the final state here? NBRT is the final state. And what is the initial state? NART. So my dear friends, this is final minus initial. This is final volume and this is initial volume. This is final number of moles and this is initial number of moles. And other things are constant. So now I can write down here P is constant. VB minus VA. Remember, this guy is constant. Now here we know already, man, NB minus NA. And remember RT. So this factor is your constant. It is not changing. There is no change in the pressure. And these two factors are also constant. And we know that VB minus VA is the final minus initial value change. This is the final number of moles minus initial number of moles. So in place of them I can write down P. Final minus initial is called as delta V. So this is your delta V. Final minus initial is again delta N. Remember, this is the change in value and this is the change in number of moles. But remember here, my dear friends, this delta N is gaseous. This is only for gaseous reactants and products. Remember, this change we have to calculate for only gaseous reactions. This change in number of moles is not calculated for solids and liquids. Remember that. So finally we have here RT. So let us call it as equation number 3rd. Let's suppose, my dear friends. Now what is the meaning of this? Have a look. This delta N, if you talk about. So my dear friends, before we talk about the delta N and all, let us further simplify it. Okay, have a look. Everybody knows that last time in previous class I derived an expression for enthalpy change. So have a look here. As we know, delta H is equal to delta U plus P delta V. That was my expression. Okay. So let us call it as equation number 4. We know that delta H is equal to delta U plus P delta V. Correct, my dear friends? Now look here. What is P delta V equal to? Have a look here. P delta V is equal to delta N RT. So this equation actually, my dear friends, I have taken from the previous class discussion, where I told you that delta H is equal to delta U plus P delta V. Correct? So now what is the use of this equation? Okay? Let me tell you. We know that we have here P delta V. Correct? And here also we have P delta V. P delta V is equal to delta N RT. So I can substitute the value of P delta V, this P delta V I am talking about. From which equation? From equation number 3. From equation 3rd into equation 4. So this equation we have already derived in the previous class, my dear friends. So I am putting the value of P delta V from equation number 3rd into the equation number 4. So I am putting this value here. Correct? So if I put the P delta value here, so what is my equation now here? Delta H is equal to delta U. In place of P delta V, I have to write down delta N RT plus delta N RT. So let us call it as equation number 5 now, my dear friends. So I have reached to the conclusion, the relationship between delta H and delta U for a gaseous reaction at constant pressure and temperature. So this is the final equation with you. Okay, if we try to summarize it in 1 or 2 minutes, it's like this. If we take the initial state of a system in which a gaseous reaction takes place, you are taking a system, okay? In that system, gaseous reaction is taking place, correct? And in that gaseous reaction, 2 moles are changing into 1 mole. Yes or no? When the number of moles are decreasing, the value will also decrease. That means number of moles are changing, value is also changing. Both things are changing, correct? But we are taking that reaction at constant pressure and temperature, correct or not? So now I wrote the initial state in terms of ideal gas equation and final state of a chemical reaction in terms of ideal gas equation. Okay, and this PRT and PRT are constant, correct, my dear friends? So only value is changing, VA to VB, and number of moles are changing from Na to Nb. Then finally I wrote final minus initial, final minus initial. So I got finally this equation, P delta V is equal to nRT. Delta and RT. Good. We have already done it in previous class that delta H is equal to delta U plus P delta V, correct? Now we know the value of P delta V here for this gaseous reaction. What is the value of P delta V? Delta and RT. So in place of this P delta V, I will write down delta and RT. So I wrote here delta and RT. And remember, what is the meaning of this delta N? It stands for the change in number of moles of what? Gaseous reactants or products. It's not related to solids and liquids. So don't calculate it for solids and liquids. So I will show you some examples where you can understand. Please make note of this. So dear friends, we have derived an equation of delta H is equal to delta U plus delta N gaseous RT. This is change in enthalpy, change in internal energy, and this is RT. That's basically R is universal gas constant and T is temperature. Correct? These two are constant. But what is the meaning of this delta N? It's important here. We know that when we derive delta N is basically change in number of moles, and it's also a state function, change in number of moles. Yes. So it will be final minus initial. We know that final state was NB and initial state was NA. And remember, it has to be gaseous and it has to be gaseous. That's important. You can also write it down. In a chemical reaction, let us suppose, my dear friends, A plus B gives me C. This is a chemical reaction. Now if I talk about, these are reactants and these are products. How many moles of reactants I have here which are gaseous? So 1 and 1. So I have 2 moles of reactants here. And how many moles of products I have here which are gaseous? You have only 1. So the formula is also final. Final will be in chemical reaction, final thing is product and initial thing is reactant. When chemical reaction starts, who will be present initially there? Reactants. And when reactants will change into products, so final state will have products. So obviously I will write down NP. It stands for number of moles of products which are gaseous minus number of moles of reactants which are gaseous. So my dear friends, the meaning is here number of moles of gaseous products minus number of moles of gaseous reactants. So let us simplify it, have a look. Let's take an example here, my dear friends. If we take this example, A plus B gives me C. This is gaseous, and this is also gaseous. Here we know that number of moles of reactants which are gaseous are how many? 2. And the number of moles of products which are gaseous are how many? 1. So what is delta N gaseous here, my dear friends? Okay, that's equal to, my dear friends, NP gaseous minus NR gaseous. So tell me, what is NP gaseous? Number of moles of products of gaseous state. It's 1 minus number of moles of reactants in gaseous state are how many? 2. So the change is minus 1. So that change in number of moles, I wrote here, the change in number of moles, or we can see the change in number of gaseous moles. Because it's only taken for the gases, not for solids and liquids. I will make you understand. So delta N is here minus 1. Let's talk about now. Let's suppose I have a reaction N2 plus 3 times H2 gives me 2 times NH3. This is gaseous, and this is gaseous. How many moles of reactants which are gaseous here? 3 plus 1 is 4. And how many moles of products which are gaseous here? That is 2. So tell me, what is delta N gaseous here? Change in number of moles, NP in gaseous state minus NR in gaseous state. Tell me, how many moles here? 2 moles minus, how many moles are here? 4 moles. So delta N will be minus 2. Now if I give you one more reaction here, my dear friends, have a look. I will take one more reaction. Let us apply heat for the calcium carbonate and break it into calcium oxide, which is solid, plus carbon dioxide, which is gas. Okay. Now we know that if I want to calculate the delta N gaseous for this, no doubt we have formula here, NP gaseous minus NR gaseous, correct? Now look here, this is solid, so we can't calculate delta N for solids. Delta N is calculated here only for gases, so for this I can't calculate, and even for this also I cannot calculate. So now when I talk of the gaseous reactants, my dear friends, how many gaseous reactants are here? 0, because reactant is here solid. So let me explain you. So this is my reactant and these are my products. Let me write down it now once again. So this is my product. So this is our reactant and these are our products. Correct, my dear friends? Now we want to calculate the number of moles of products which are basically in a gaseous state minus number of moles of reactants which are in gaseous state. How many moles of products are in gaseous state? This guy is in solid state, so you have to neglect it, cross it. Only 1 mole is here, so you have 1 mole, okay, of product in gaseous state. So this 1 mole is basically gas. So the number of products in gaseous state are only 1, because this is solid, so you have to neglect it. So 1 minus. How many moles of reactants are in gaseous state? Nothing, because this is in solid state, so you can't take it. For solids and liquids, okay, we are not calculating delta N. Delta N is calculated for gases only. So how many reactants are in gaseous state? Nobody, because there is only 1 reactant and this reactant is in solid state. So cancel it. So the number of reactants in gaseous state are only 0. So the value is 1. So delta N is basically 1 for this. Because delta N is here the change in number of moles of reactants or products. Yes or no? With respect to what? With respect to gases. It's not with respect to what? Solids and liquids. If I give you one small example as well, okay, have a look here. If I have a physical process also with me, water liquid is converted into water gas by applying the heat. So this is not a chemical reaction, this is a physical process. This is a physical process. In this physical process, if I want to calculate delta N gaseous, yes or no? So that is NP. Here we don't have a product, we can write down N final, or we can say, yes, N final minus N initial, because these are not products. This is not a product and this is not a reactant, because it's a physical process. So N final minus N initial. But final should be also gaseous and initial should be also gaseous. So finally we have water in gaseous state. How many moles? 1 mole minus the number of moles at initial state are how many? 1. But they should be also in which state? Gaseous state. That means your initial number of moles. These are your initial number of moles. Let's suppose this is initial, I will write down this is final, okay? So initial number of moles should be in gaseous state, but it's a liquid state. So it will not be taken in consideration. If it is gas, then I will take 1 mole here. So 1 minus 1 will become 0. But it's liquid, so you have to leave it. Yes? So how many moles of, you know what? The water are basically in the gaseous state at the initial state. 0, there is no gas here, so 0 here, so 1. So I hope you are understanding, my dear friends. So delta N is only taken for, okay, number of moles of products in gaseous state minus number of moles of reactants in gaseous state. And for solids and liquids, it's not applicable, because I told you last time that the change in volume of solids and liquids is insignificant when you apply the pressure onto them. Please remember that particular point and make note of this. Friends, do take care of yourself. Have a great time. Catch you in the next class. Yo-yo.